Welcome to this lecture. In the last lecture, we were discussing about a black box testing technique known as the boundary value testing, and we had said that this is a general risk. The boundaries are at general risk of errors, and therefore, we must define test cases based on the boundary values. Let us proceed from what we were discussing last time. Let us say we have a code where depending on the applicant age, we make the higher status is either no, do not hire underage, or higher status is part time, full time, and overage higher status is no. We can identify the boundaries here, which is between these two equivalence classes. 16 is the boundary, and if we select the boundary, we are likely to determine the bug here that 16 is included in both the equivalence classes. Similarly, 18, 55 and so on. And then we can correct our code where we have the boundaries clearly specified here, 0 to 15 do not hire, 16 to 17, 18 to 54 and so on. And then we can take care of values that are invalid, and we need to take care of the boundary between the invalid and the valid set of equivalence classes. So, based on the boundary values, we have the corrected code, and then what if for this code we have, let us say, -1, that is not addressed here in the code, and therefore, it will generate a failure. Depending on the 4 equivalence classes here, we can define the boundary values here. For the first one, -1, 0, 1, 14, 15 and 16. For the second one, 17, 18, 19, 17 at the boundary of this. So, there are basically, if we look at here, we have one boundary that is less than 0, another boundary here at 15 and 16, and another here at 17 and another here at 54 and so on. We must include the boundaries here. For each boundary, we take a test case which is just on the boundary, one on the higher side and lower side and so on. So, these are, each of these is a test case. And once we identify the boundary values, then we need to define the test cases. These are the valid set of equivalence classes, invalid set of equivalence classes, and we already had selected one representative value for the equivalence class testing. Now, we will select values on the boundary for the boundary value testing. Let us look at some example problems. Let us say, let us take the same problem that we were considering earlier for equivalence class testing, that it takes one parameter only. The valid values are between 1 and 5000. If we draw this, we represent the data, then we have one valid class and 2 invalid classes, and there are 2 boundaries here. One is between the valid class and the invalid on the lower side, and another is between the valid class and the invalid on the upper side. We include the boundary 1 and one element, one test case which is less than 1, which is 0, one element which is valid. So, it can be 2. Similarly, 5001, 5000 and let us say 499, 4999. So, these are the set of test cases for one parameter which is a range of values between 1 and 5000. Now, let us look at age as a parameter, and the valid age range is 1 to 150. Here we have 3 equivalence classes. One is a valid equivalence class which is between 1 and 150, and there are 2 equivalence classes. So, for boundary value testing, how many test cases do we need? Of course, we need to include the boundary, the boundary value, one below the boundary value, above the boundary value, and of course, we can combine these two. We can select a value anywhere here. So, there will be at least 5 test cases, at least 5 test cases for boundary value testing. So, the 5 test cases at the minimum boundary, immediately above the minimum, between the minimum and maximum, immediately below the maximum, and at the maximum boundary. Just an example, predict longevity, and age is the parameter, and age is between 100 and 150, and once we identify the 5 boundaries, 5 boundary values, you can represent them 1 to 45, 149 and 150, and these form our boundary value test cases. But what about multiple parameters? For each of the parameter, we might identify different boundaries. And let us say for parameter years of education and let us say age, we identify different boundaries, and let us say the boundary values for the years of education is 1, 2, 12, 22, 23. These are the boundary values for years of education. Similarly, 1, 2, for the age we have 1, 2, 37, 149 and 150. These are the boundary values. Now, how do we define the test cases? By combining these two boundaries. One way is that we just represent each of these in the test case and take any one of the value from the other equivalence class for the other parameter, and similarly we define test cases corresponding to each of the boundaries here and some value of the other boundaries. So, pick one boundary from here, the first parameter, and combine with all other parameter boundaries here, and similarly for every value on the boundary on the first parameter, we take any value from the second parameter like 37 or something. So, what will be the number of test cases that will be required? If there are, let us say, m here, m boundary values for the first parameter and n boundary values for the second parameter, we will have m plus n minus 1, because 1 is common here. Therefore, we will have m plus n minus 1. And we represent the same thing here. This is for two input parameters, and we define the boundaries here. Let us say for the first parameter we define there are 5 boundary values, and for the second parameter also there are 5 boundary values, and this is common here. For the first parameter, these two are the boundary, and this is a point just inside, and these are the 2 points on the boundary, and this is just inside. Now, if we combine these two parameters, we take this one, this one, this one, these two, and therefore, we get 9 test cases, and we can represent it as 4 z, where z is the number of parameters plus 1, because for every boundary we have 4 and 1 representative value here, and similarly for the other one 4 the boundary and 1 representative value, and therefore, we will have 4 z plus 1, which is the number of test cases required. Let us say we have a function f x y, the function f takes 2 parameters, 2 integer parameters x and y, and x takes value between a and b, and y takes value between c and d. Now, how many test cases are needed? If we represent the boundary here, we have a boundary at c, we have boundary at d, we have boundary at a and b, and just above we have test cases and 1 representative here. So, it will be 4 into 2 parameters plus 1, which is equal to 9. There are 2 parameters here, and each one we need 4 and 1 is the common, and therefore, we need 9. All the weak testing that we have been discussing with respect to equivalence class, multiple parameter equivalence class and boundary value, the weak testing actually implicitly assumes a single fault, that is only one of the parameter can have a fault. If that is the assumption, then weak testing is all right, because for every input, every representative of one parameter, we combine with the representative for the other parameter. Therefore, if this is the let me just explain this, that if we have 2 parameters for weak testing, if you remember, if there are let us say 3 equivalence classes for the first parameter and 3 equivalence classes for the second parameter, then we may select this, this and this. So, we have all the parameters of all the representatives of the parameter 1 and parameter 2 represented in our test cases, and therefore, if there is a fault in any parameter, representative parameter, that will be detected. But what if specific combinations of parameters have fault? Let us say when parameter 1 has representative from this and the corresponding one is here. If these two are chosen, then there is a fault. Of course, weak testing will not be able to detect that. It will detect only when one of the parameter, any one of the parameter, if we select a value there, then it is faulty. In those cases, weak testing is satisfactory. Otherwise, we need to go for strong testing. Now, let us look at the robust testing. In robust testing, we need to include a value which is invalid. Let us say we have a function called as ASCII to integer and it takes a string, let us say character it takes, and it gives us a integer value for that. And if we look at the ASCII table, that 0 to 9 are the characters that are valid, which are the valid characters for integers, and they have values 48 to 57. But then if we give a invalid value such as slash or colon, then we can check that it gives us a wrong value, and therefore, we must include the one which is invalid integer representation, and that we call as the robustness testing. For robustness testing, therefore, we consider the invalid values as well, and therefore, the number of elements at the boundary are 3 on each of the boundary. For x, the parameter 1, we have 2 boundaries, and for both boundaries we need to select 3 element each, and similarly for parameter 2, for parameter 2 we need to select 3 elements each. For parameter 1 we also select 3 element each, and then this is the general element with which we combine, and therefore, we need 7 test cases for each input. If we have n test cases, if we have n parameters, then we can easily compute how many test cases we need. The main idea behind robustness testing is that, do we anticipate the error situations? Do we display informative error messages when the value is invalid? Is there some kind of recovery from the error? So, those are the main objectives of the robustness testing, to check whether the programmer has handled invalid values satisfactorily. Considering invalid values as well, we see that for 2 parameters, we need 13 test cases. So, 6 plus 6 plus 1, 13 test cases. So, in general, if we have n parameters, we need 6 n plus 1 test cases. But the main problem with boundary value testing is that if we have a set of values, we do not have boundary there. What about Boolean values? There also we do not have boundaries. What about radio buttons like this? These can be considered like Boolean variables, either they are on or off. Here also we do not have boundary for this, cannot be defined. What about a non-numerical parameter, let us say character string? Again, it is hard to define boundaries for that. Now, let us conclude our discussion on the equivalence class and boundary value testing, but before that let us do a small quiz. Let us say we have a function which solves the quadratic equation of the form a x square plus b x plus c. The name of the function, let us say quad solver, and it takes 3 parameters a, b, c, and it returns the roots. What will be the equivalence classes for this? If we examine the scenarios here, then one is that the root may be complex, the root may be real. If it is real, it may be coincident or unique. The valid set of values can be classified. The equivalence classes will be for complex root, real root, and the real root can be coincident and unique. And we can also have the invalid set of values and so on. Now, let us look at combinatorial testing. We will see that if the number of parameters to a function is large and it uses many global variables and so on, the number of test cases required for equivalence class testing and boundary values testing can be large, and we will see how to handle that problem. And let us look at combinatorial testing. The behavior of a program is affected by many factors. How many input parameters are there, how many global variables are there, state variables, and so on. And for equivalence partitioning, we identify for every parameter what are the equivalence classes, and when we combine it, we saw that there is a weak testing, strong testing, and robust testing. And if we do a robust testing, then it may become impractical if the number of input parameters are many. But then in many situations we find that the number of input parameters are actually too many, especially in controller applications and user interfaces. Let us look at this specific user interface. Just see how many parameters are there, input parameters, there are just too many, and if we combine the equivalence classes here, then we will get too many test cases. For combinatorial testing, we will see the decision table based testing, cause effect graphing, and pairwise testing, which will help us to handle a small number of test cases when we have many parameters or many different types of inputs. First, let us look at the decision table based testing. The decision table based testing is applicable when there are many conditional actions. Here we develop a table, and in the table we represent the conditions represent inputs, and then the actions represent the output, and each of these column on the table is called as a rule, and the rules are the test cases. Let us see how to generate the decision table, and then once we generate the decision table, we can easily form the test cases. Each of the column will become a test case. Let us take the example of this condition here. C1 and C2 or C3, then A1. You can observe here that C1, C2, C3 are the input and A1 is the output. We write here the input C1, C2, C3. These we call as the condition, and then we have the action, and we combine all possible values of the condition with the action. And let us say the condition is for C1 it is true, C2 is true and C3 is true. C1, C2, C3 are all true, and then the action is A1. We can look at the expression here. Now, what if C1 is false, C2 is true and C3 is true? In this case, it is also A1. Now, what if C1 is false, C2 is false and C3 is true? Again here this is A1, action is A1, but what if all are false? Then there is no action, and so on. We can complete this table, and this is the decision table, where the top part of the table contains the condition outcomes, the lower part this displays the corresponding actions, and each of the row is a rule and they form the test cases. So, as many rows will be there on our table, those many test cases we will need. So, this is a test case, this is a test case, C1 is false, C2 is true and C3 is true, and so on. We are almost at the end of this lecture. We will stop here and continue our discussion from this point. Thank you.